In this lesson, we are going to introduce notation for a time series and a lag or backshift operator. So we'll formally introduce a time series with notation that will allow us to talk both in theory and in practice at an abstract level without having to show the numbers of the time series all the time. And the operator that we are going to introduce allows us to do a very common operation with time series, which is lagging the time series. That is the backshift operator. We learn our code that will lag the whole time series for us, and that our code is going to be posted separately, most of it. Why is it important to know all this? Well, because it's nice to have a language, mathematical language that we can use when we talk about the time series. And it's important that we understand the language, and the language is common to all of us. And backshifting or lagging a time series is the process behind the concept of autocorrelation that we'll see in a future lesson. And also, lagged values of a time series appear often in time series models. So it's important to know what they are. So let's look at the mathematical definition of a time series. In practice, a time series, denoted by lowercase y sub t, the observed time series, time t equal 1, 2, 3, is repeated observed measurements of the value of the variable y for the same entity. If it's a country, it could be income measured every quarter. If it's a river, it could be just the flow over every week. If it's the atmosphere, it could be contamination every hour. Chemical process could be some other measurement measured every single minute. And usually we observe over time to observe changes over time. That's the goal. Abstractly, from a probabilistic point of view, a time series is a stochastic process where t is time and the k is known as the lag. Okay, so we observe the time at time t, the time series at time t, t minus 1, t minus 2, t minus k. K means lag. The observed time series that we usually have in our hands is just a particular observation of the stochastic process. We only have one time series. So let's see what that means. That means in practice, we find ourselves with a time series that we want to analyze. We found our data, we have the time series, for example, the number of undergraduates in Minnesota between 1998, Q1, and the Q3 of 2021. Here is a few lines of a much larger data set. On the right-hand side, we have the stochastic process, several realizations of the stochastic process. So each of these curves here, each of these sequences is one time series. What this is saying is that the time series from a probabilistic point of view is a stochastic process. It's random, and it could result in any of these particular sequences, and we only have one. This notion of having one observation from a population, and you can consider these numerous sequences from the stochastic process as depopulation from which we are drawing our observed time series. It's called the ensemble population. Well, this notion of just having one observation is kind of alien to us because in statistics, we are being told all the time that you want to have a large sample, right? So you will say, well, I mean, if one observation is one sequence, why don't we have a much larger sample? Why don't we get more time series? Well, in life, we only have a chance to observe one time series. We cannot go back and start the process again, right? So that's what makes time series a little bit less intuitive than other statistics random samples, right? In a typical random sample statistic, we expect, oh, increase the sample size. Fine. Well, here, we only have one observation, one sequence, but that's where the theory of time series is going to come in and help us, okay? So keep that in mind. We could have observed any of these. We just happen to have observed just one of them, okay? And we'll get back to it when we study theory in another lesson. So for example, suppose the stochastic process is an autoregressive process of order 1. And we learn these models in future lessons. And let's say the model is yt, means the observed value at time t equals, it's a function of the value observed at time t minus 1 plus some random term. And we're going to assume that the random term is Gaussian. Well, the same model, this model could generate many time series. It will depend on what the random process is, right? So for example, we could have all these very different time series generated by the same model, right? It could be y1, y2, y3, y4, and we have thousands more that could have been observed. So this is the ensemble, parts of the ensemble, some elements. These are some observations from the ensemble or population or possible time series that could be generated by this autoregressive model, right? So we generated this using simulation. So we created first a space to put the 4 pictures. We could have put more, and you can generate more with this code, and yours will look different. Please do not use seed, because the nature of a stochastic process is not that it's a seed. You use a seed for replicability. But if you want to see different ones, you don't want to use seed. So the first one, the y sub 1, is generated by this code. First, we generate the random numbers that are Gaussian from a normal, 0, 1. And then we are going to generate the model. And that gives us the first series y1. Then we generate the second series. Notice we are not using seed. Each time the random process is different. So we got a second one. Then we have a third one, and then we have a fourth one. And then you close this window using divide.off if you want to close it in R. So this is just the code to generate an ensemble of time series produced by this stochastic process. Okay. And then in practice, we might observe just one, right? That's life. We don't have unlimited life times. So let's say we observe this time series again. This is the observed value and of this random variable, number of undergraduates in Minnesota. And let's say we are a star. Let's say we focus on time t equal 4. Okay, notice that t equal 4, 1, 2, 3, 4, 5. It's just for us to understand ourselves. It's just for the calculation. It's just for the theory. In practice, we have a time stamp. We need to know what the value of t is associated with in terms of the time stamp. But for theoretical discussions, we need to have the t clear. The little t is our index, right? So our time t, let's say we start at time t equal 4, which is the 4th quarter of 1998, right? So we are here. Suppose we are here, and the value is 170.242 for y. So we say y sub 4, and again, this is the notation we use, y sub 4, or you could replace it with y sub 1998 Q4. But for modeling, we use this notation, little t. It will be for writing our models. And then, so that means that y sub t minus 1, y sub t minus 1 will be y sub 3, right? If t is equal 4, then y sub t minus 1 is y sub 3. And that will be the value 147,838, right? Y sub 3, right, is 147,838. We can see that in the column of the y sub t. Then what we did to the time series to obtain the value is apply the backshift operator. So we say this is the b of, I should say here, y sub 4, right? B backshift of y sub 4 is y sub 3. And but we define t here, so that it's implicit, right? Because it's t4. So this is the backshift operator applied to y sub t. Okay, and then y sub t minus 2, right? If t is 4, it will be y sub 2, and that's 1, 2, 3, 1, 2, 1, as shown in the table, and that will be the second power of the backshift operator. And so the second power of the backshift operator for yt will be the same as the first power applied to yt minus 1. Okay, so that's, I'm introducing informally now the backshift operator. And then y sub t minus 3 will be 198,281. Okay, we could do y sub t minus 4, but notice that y sub t minus 4 will not have any observations. We don't have any observations for y sub t minus 4, right? So it will not be practical. So let's introduce the backshift operator more formally. The backshift operator shifts or lags the subscript of the time series, the index, right? Subscript of the time series backward in time by 1 period. So if the data is annual, it will be a year. If it's monthly, it will be a month. It will put us 1 month behind. So the backshift to the first power just lags the variable by 1, okay? For example, the backshift applied to a time series that we observe at time t equal 50 will be y sub 49. So that means the backshift operator, right? So y sub t minus 1 here is y's observation y at index 49, okay? And raised to the power k, shifts lags the subscript of the time series k periods. So b to the power k of a time series observed at time t equals y sub t, the same, the value of the time series at time t minus k. Okay, so for example, if we do this, which we do often sometimes later on when we have seasonal monthly time series, we might just be interested in the 12th power, right, of the backshift operator, lagging the series by 12. So lagging the series that we observe at time t equal 50 by 12 puts us in the value of the time series at time t equals 38. Okay, so that's how the backshift operator works. And so let's see, we apply to the Johnson data set in R, which is a time series that comes with the datasets package of R. And it's already a TS object, and we have already introduced it earlier in earlier lessons. So let's consider the first 4 years of this TS object. So this will be our y sub t, okay? So the point now is, okay, if we want to shift a whole time series 1 lag, how do we do it? So this is the data at time t, right? The observed data. But now let's say we want the time series that is reflecting the t minus 1 at every point in time reflects yt minus 1. So notice that yt minus 1, right? So for if you start at 1960 quarter 2, then yt minus 1 is the yt at time quarter 1, right? So 0.71. If you want the time series, each value of the time series at t minus 2, then if you start at quarter 3, you have to start quarter 3, yt minus 2 will be the first quarter observation, right? And quarter 4 observation will be the value of the time series at quarter 2, 0.63, okay? So notice how as we represent a time series at a particular point as the lag values of the original series, we are sort of creating less data, right? Each series is gonna be shorter and shorter. So yt minus 3 is gonna be starting at quarter 3 with the first value of the original data, and then yt minus 4 will start in the next year, right? Notice how we start in 1961 with the first observation of quarter 1 of the original data, okay? So if you put that together, notice what's happening. What's happening when you combine all these time series is you have the original time series, which in the R code posted separately, we call JJ, and these are only the first years, right? The first 60, 61, 62, 63. And there is more data, of course, as you know. So the lagged series, okay, so this is the yt, this is the yt minus 1, is the JJ backshifted, okay, is yt minus 1, has to start at quarter 2 because we don't have observations before quarter 1. The y sub t minus 2 has to start quarter 3. So notice how we introduce missing values, right? And so if we had to calculate the correlation between yt and yt minus 1 variable, we could not use the first line of data, right? So later on, we are going to calculate the correlations between these columns to calculate autocorrelation. And NR is going to use as much data as possible. It's going to be using as much as it can for each pair, okay? But we'll illustrate this in a different way, in a more friendly way, before we introduce autocorrelation. But autocorrelation is going to be calculated with a data set like this, okay? So we end up with this data after we lag the time series. And of course, there are more years. I just didn't want to put a whole data set here. The point is just to illustrate what the backshift operator is doing. So notice I denoted in the R code jj.b2 means backshifted to the second power, yt minus 2 backshifted to the third power. And what I'm going to do now is just create a complete data set, right? So I want to review correlation with you and in the next lesson. And in order to do that, I simplify the discussion a little bit and ignore what we are going to do, which is use this data set on the left-hand side and just pretend that we have a complete data set. And of course, this is a much longer data set. I'm just illustrating that complete cases start in 1961, right? Because we don't have missing values. And then at the bottom of the data set, we are going to cut it also where we start having missing values because so when you run the code, you might want to see the whole data set, okay? So we remove the NA to have a complete data set just to illustrate correlation between two variables in the context. But notice that we can do better if we calculate correlation with more observations. So if we do it pairwise, well, right, yt with yt minus 1, yt with yt minus 2, we want to use as much data as possible. And that's what I really do when we calculate the autocorrelation. So that's what we'll do in the next lesson. So lagging a time series using the backshift operator gives us the value of the same time series, but at a different time stamp, as we have seen, right? And if we lag a time series at different lag scale, we can obtain a data matrix that looks like our typical data set that we are used to work with, several observations, several variables. Those are the rectangular data sets that we usually learn in introductory statistics classes. And with that data set, now it's going to be easier for us to understand autocorrelation introduced in the next lesson. So we created a complete data set only for illustration purposes. In practice, when we are going to compute the autocorrelation function of a time series, we are going to be using as much data as we can, and that's what the ACF does, okay? So this completes this lesson, and we hope you enjoyed it, and we will talk more in the next lesson about correlation between pairs of these variables that we created with the backshift operator.